notes are about exponential modeling. Our goal for these notes is to be able to use an exponential function in different real-world situations to model either growth or decay, just like we talked about in class today. First off, we want to recall the general form of an exponential model, and we can say that some function, f of x, is equal to a times b to the x. And we talked about how b is our growth or decay factor, and we know that if b is bigger than 1, it's going to be growth, and if b is less than 1, it's going to be decay. We also know that b is not allowed to be 1, otherwise we just have a very boring function, it would not be exponential, and also b has to be positive. We're not dealing with negative b values here. Also, this a value we mentioned was, when we graphed this, was the y-intercept of the function. Think about plugging in 0 for x. F of 0 is a times b to the 0, and of course b to the 0 is always 1, so that's just a. So instead of calling it the y-intercept, because in this set of notes we're not going to be doing any graphing actually, we're just going to be talking about how we can model using equations. So instead of calling it the y-intercept, the real world kind of meaning for that would be an initial amount. So at time 0, or when x equals 0, we have a things. So I'm going to call it the initial amount. And that'll become clear when we talk about some real-world scenarios. So we know if b is bigger than 1, it's growth, and we can talk about certain percentages growth or certain percentage decay. And let's see if we can figure out how we model some situations. Here's our first situation. We're talking about a population of monkeys, and we know that each year, that word annually is telling us that each year the population grows by 12%. So I know that the percent increase or percent growth is 12%. I guess I should, since I called it percent growth, I should call it 12%. In decimal, of course, that is 0.12. So population of monkeys is growing by 0.12. If there were 400 monkeys in the year 2000, how many monkeys will there be in 2043? Let's figure out what our growth factor is. Since our percent growth is 0.12, our growth factor, since it has to be bigger than 1, is 1.12. And that, of course, is our b value. Our initial amount is actually given, which is our a value, and that looks to be 400. So our equation actually kind of falls right out of this information. The number of monkeys, I can call that y, is equal to 400 times our growth factor, 1.12, to the power of however many years we want to go into the future. So if I wanted to know after 1 year, I would just multiply 400 by 1.12 once. If I wanted to know after 5 years, I'd have to multiply by 1.125 times, which is the same as multiplying by 1.12 to the 5th power. So that's why we're talking about exponentials here instead of just linear things. So now let's look at what we actually need. The year, kind of starting year, was 2000, and we want to know in 2043. So that is 43 years after our starting time. So this would mean that we want to plug in 43 for x. Notice I'm not plugging in 2043, I'm not plugging in the year. I just want to know how much after our initial year. Since our initial year was 2000, we just want 43 as our input. 400 times 1.12 to the 43, and I'm going to use my calculator for that, and I would enter it just like you see on the screen, 400 and then parentheses 1.12 raised to the 43rd power, and I get 5291.9. So I'm going to round that to 2092. I'm going to round to the nearest monkey. Since we're talking about monkeys, I think it makes sense to round to the nearest monkey. If we were talking about money, I might think otherwise. That's all we did. We came up with our equation and we plugged in. Let's look at this problem. It's a little bit different. Sam's car's value depreciates at a rate of 62% each year. He bought his car 8 years ago at a cost of $19,000. How much is it worth today? The first thing I notice is this word depreciates. We have to know what that means. That means that it's decreasing in value, which means that we're going to be talking about decay instead of growth. And since we're decaying by 62%, that would mean that to find our decay factor, I would have to subtract 62 from 100. I want to know what percent do we have left. If we're decaying by 62%, then our decay factor, or our B value, just like we saw in class, is 1 minus 0.62. 1 minus 0.62 gives us 38%, or 0.38. So that's our decay factor. Decaying by 62% means that we're multiplying each year by 0.38. And our initial value is 19,000. Our decay factor is just 0.38. We want to make sure that we're getting smaller and smaller and smaller amounts. And he bought his car 8 years ago. So after year 0, which is when it cost $19,000, 8 years later would be today. So I want to multiply by 0.388 times, or 0.38 to the 8th power. Again, I'm just going to put that into the calculator, times 0.38 to the power of 8, and I get 8.260, etc. So I'm going to round to the nearest hundredth because we're talking about a car's value. So it makes sense to have cents in there. I can call that $8.26. We can have hundredths of a dollar, so I think it makes sense to round to 2 places after the decimal. That might seem a little silly. I don't think that's very real-world accurate. I don't think your car is only worth $8.26 after only 8 years. But in terms of the question, if we're really, truly are depreciating at 62% each year, then yeah, after 8 years, it seems as if mathematically our car is worth about $8.26. Let's do one more type of modeling problem, and this one doesn't have much of a real-world context, but it's still very important. We need to write the equation for an exponential function that's passing through 2 points. We've seen questions like this before when we had like parabolas or, I don't know, cubics or square root functions, but let's see how we might approach this with an exponential model. Don't forget, here's our general form. Of course, I could have a shifted exponential, but I want to make life easiest as possible. So if I don't have to write a shifted one, I'm not going to. Let's just try to force this, these 2 points to lie on a non-shifted, just regular y equals ab to the x function. We have an x and a y, and another x and a y. So the first piece of information tells us when x is 3, y is 1. Which can be represented by writing 1 equals ab cubed. When x is 3, y is 1. I just plugged in both of those things. Let's do that for the other point. When x is negative 2, y is 32. So now I have 2 equations, 2 variables, a and b. This is really a system of equations. There's many, many, many different ways to solve this system. I'm just going to show you one method. Maybe in class we'll talk about another method as well. But we're just trying to figure out, based on these 2 sentences, what does A equal and what does B equal. I'm going to work with the first equation. And I notice that 1 equals ab cubed. And I'm going to solve for A by dividing both sides by b cubed. So I now have that A equals 1 divided by b cubed. I just solved for a. I still have a b on the right-hand side. But now I can take that and substitute in for a over here using substitution. 32 equals a times b to the negative 2. We're using substitution. Now I have one equation with only b's in it. But it's kind of still a little nasty looking because I see b to the negative 2. I know that b to the negative 2 is the same as 1 over b squared. And I know that if I'm multiplying fractions, I can multiply numerators and multiply denominators. So I now would get that 1 over b to the 5th is equal to 32. Remember, b cubed times b squared equals b to the 5th. So that's how I simplified that fraction. Now I can put this over 1 and I can cross multiply. And I get that, I'm actually going to move to the left here. I know it's going to be a little crunched in, but I get that 32b to the 5th is equal to 1, which means b to the 5th is equal to 1 over 32. How could I solve for b? Well, I could take the 5th root of each side of the equation, but I actually don't even really need my calculator for this. I want to think about what number raised to the 5th power gives us 1 over 32. And that number 32 is a big clue because I know that 32 is 2 to the 5th power. So b is equal to 1/2. I just kind of reasoned through it. I know that 1/2 times 1/2 times 1/2 times 1/2 times 1/2 is giving us 1 over 32. If you couldn't reason that through in your head, you could always use your calculator and take the 5th root of each side. Your calculator can do 5th roots, you just have to figure out how. We're not quite done because we have b, but now we have to find a. So I'm going to use what's in the green circle to plug back in. A equals 1 over b cubed. 1/2 cubed is 1/8. 1 over 1/8 is a. 1 divided by 1/8 is just 8. So we have our b, we have our a, we can write our exponential model. I'm just going to write it right at the top here. Y equals a times b to the x. This was our final answer. Again, all we did is we solved a system by using substitution, and there's more than one way to do this. Maybe you can play around with it. Maybe it was a little easier to start with the second equation and solve for a and plug back into the first. I don't know, whatever you find easier, you can do. So there's just a few examples of how we would use exponential models to solve real-world examples. Sometimes there's a context, sometimes not. We just have to be very careful about paying attention to percentages, to growth or decay, and initial values. Good luck!